Students, the objectives of today's lecture will enable you to understand the concept of isomerism. We are going to discuss the types of isomerism, in which we will study structural isomerism and stereoisomerism. Let us start with the definition of isomerism. The definition of isomerism says that compounds having the same molecular formula but different chemical structures are called isomers, and the phenomena is called isomerism. Since they have same molecular formula, the difference in properties must be due to the different modes of combination or arrangement of atoms within a molecule. Let us study the classification of isomerism. Isomers are classified into two main branches, which are structural isomers and stereoisomers. The structural isomers are classified into five main classifications, which is chain isomerism, position isomerism, functional group isomerism, metamerism, and tautomerism, whereas stereoisomers are classified as conformational isomers and configurational isomers. The configurational isomers are further classified as geometrical isomers and optical isomers. Now students, we are going to discuss all these isomers in detail. Students, let us start with the definition of two main branches of isomerism. The first one is structural isomers. When isomerism is due to the difference in arrangement of atoms within a molecule without any reference to space. Over here, space means the three-dimensional space. The phenomena is called structural isomerism, or in other words, we can say structural isomers are those compounds that have same molecular formula but different structural formulas. Structural isomerism is of five types. The first one is chain isomerism, position isomerism, functional group isomerism, metamerism, and tautomerism. The second main branch is stereoisomers. When isomerism is caused by different arrangement or orientation of atoms or group of atoms in space, this phenomena is called stereoisomerism. The stereoisomers have same structural formulas but differ in arrangement of atoms in the space. Or in other words, we can say stereoisomers is exhibited by such compounds which have same structural formula but differ in configuration. What is the meaning of configuration? The term configuration refers to the three-dimensional arrangement of atoms that characterizes a particular compound. Stereoisomerism is of two types, geometrical, or it is also called cis-trans isomerism, and the second one is called optical isomerism. Now students, let us try to understand all these isomers with example, starting with structural isomers. In structural isomerism, the isomers have same molecular formula but differ in structural formulas. The structural isomerism is of five types. The first one is chain isomerism. Chain isomers have same molecular formula but differ in order in which the carbon atoms are bonded to each other. For example, N-butane and isobutane. Now students, both of these isomers have same chemical formula, that is C4H10, but you can see the difference in the chains. N-butane is a straight chain structure, whereas isobutane is a branch structure. You can see the difference in connectivity of the bonded atoms. The next example of chain isomerism is 2-methylbutane and 2,2-dimethylpropane. These two are isomers of each other. As you can see, 2-methylbutane, or we can say isopentane. Iso means one carbon atom will be attached to the chain on second carbon atom. The next isomer is 2,2-dimethylpropane. It is a neo structure. Both of these isomers have same chemical formula, but you can see the difference in the chains. Both of them is a branch structure, but this is a neo structure and 2-methylbutane is a iso structure. So the difference is in the carbon atoms which are bonded to each other. Now students, the second type of structural isomers that we are going to study are position isomerism. Position isomers have same molecular formula but different in the position of a functional group on the carbon chain. For example, you can see 1 bromobutane and 2 bromobutane. The chain comprises of 4 carbon atoms in both of these isomers. But what is the difference? The difference is in the functional group which is attached to the chain. In 1 bromobutane, this bromine atom is attached to the first carbon atom, that is why the name is 1-bromobutane. Whereas in the second isomer, it is attached to the second carbon atom. That is why it is called 2-bromobutane. So you can see the difference in the position of this functional group in both of these isomers. That is why it is called position isomerism. The next example is N-propyl alcohol and isopropyl alcohol. Now look at the attachment of alcoholic functional group. In N-propyl alcohol, the alcoholic functional group is present at the terminal atom, at the first carbon atom of the chain. Whereas in isopropyl alcohol, it is present on the second carbon atom. So you can see the difference in the position of the functional group in both of these isomers. That is why it is called positional isomerism. The third structural isomers that we are going to study are functional group isomers. Now functional group isomers have same molecular formula, but they are different in the functional groups. For example, acetone and propanaldehyde. Now students, you will see that both of these isomers have same chemical formula. As you can see, 3 carbon atoms, 6 hydrogen atoms and 1 oxygen atom. Similarly, in this molecule, you are having 3 carbon atoms, 6 hydrogen atoms and 1 oxygen atom. But this is a acetone, a ketone, whereas the other isomer is an aldehyde. So the difference in the structure is that both of these are different functional groups. One is a ketone and the other one is aldehyde. Although the molecular formula is the same, but functional groups are different. Such isomers are called functional group isomers. The second example is acetic acid and methyl formate. Again, you can see you are having same molecular formula in both of these isomers, but the difference is in the functional group. Acetic acid is a carboxylic acid, C double bond O OH, whereas methyl formate is an ester, C double bond O OR. So you can see you are having different functional groups in both of these molecules, but the molecular formula is the same. The next structural isomers that we are going to study are metamerism or metamers. This type of isomerism is due to the unequal distribution of carbon atoms on either side of the functional group. Students, some functional group are not terminal. They are present in the middle of the hydrocarbon chain. So if there is unequal distribution of the chain across the functional group, they are called metamers, and the phenomena is called metamerism. Members belong to the same homologous series. For example, this is 2-pentanone, 1, 2, 3, 4 and 5. And the ketone functional group, this carbonyl is present on the second carbon atom. So it is 2-pentanone. The metamer of this 2-pentanone is 3-pentanone. You can see that the number of carbon atoms is the same, but the position of the ketone carbonyl is different. It is at 3 position in this isomer. Similarly, another example is diethylamine. Across this amine group, both of the chains are ethyl radicals, but the isomer is a little different. It is methyl propyl amine. Methyl on one side and propyl on the other side, but all together there are 4 carbon atoms. So distribution of the carbon atoms across the functional group is different in metamerism. Another example is diethyl ether, ROR. This is an ether. The metamer of diethyl ether is methyl propyl ether. Over here you are having a methyl group, and on the other side we are having a propyl group. But you can see that the number of carbon atoms, hydrogen and oxygen, are same in both of these structures. Students, the last type of structural isomers that we are going to study are tautomers. This phenomena is called tautomerism. This is a type of isomerism in which a compound exists simultaneously in two forms in equilibrium with one another. It involves the shifting of the position of proton, means intramolecular shifting of proton or hydrogen is going to take place. This type of hydrogen atom is also known as mobile hydrogen. Look at this keto form. This hydrogen is going to change its position and transfer into an enol form. Look at the open structure of this keto form. The lone pairs of oxygen is going to make a bond with this hydrogen atom, and the bond between carbon and hydrogen is going to shift between these two carbon atoms, making a double bond. So a bond is formed between oxygen and hydrogen over here, as you can see this OH bond, and a double bond is created between these two carbon atoms. This is called enol form. Why? Because an ene is present, a double bond, and ol is present, a hydroxyl group, together at the same carbon atom. That is why it is called enol. This is the keto form. You can see the ketone functional group, and this is the enol form. They exist in equilibrium due to the transfer of this proton within the molecule. This type of isomerism is called tautomerism. The second main classification of isomerism is stereoisomerism. When isomerism is caused by different arrangement or orientation of atoms or group of atoms in space, this phenomena is called stereoisomerism. The stereoisomers have same structural formulas, but the difference is in the arrangement of atoms in the space. Stereoisomerism is of two types. The first one is geometrical, which is also called cis-trans isomerism, and the second one is optical isomerism. Now students, let us start with geometrical isomerism. Geometrical isomers are also called as cis-trans isomers because they have same structural formula but different spatial arrangement of atoms, means the atoms which are arranged in the three-dimensional space. The carbon atoms of alkenes are sp2 hybridized, making a sigma bond and a pi bond. Cis-trans isomers result from the restriction of rotation across the double bond in alkenes or about the single bond in cyclic compounds. Because of the restriction in rotation in both of these structures, cis and trans isomerism is possible because across this double bond do not have a free rotation. So the groups which are present on the above of this double bond remains on their fixed position, and below the double bond also remains at their fixed position. And cis isomers are those which are having identical group of atoms on the same side of the double bond. And trans isomers are those which are having identical groups on the opposite sides of the double bond. Similarly, you can see the cis isomerism in the cyclic structure. The two identical groups are above the plane in cis isomerism, whereas in trans isomerism, these two identical groups are present on opposite sides of the plane. Students, let us look at some important structural features which are required for geometrical isomerism. The first one is the presence of pi bond which lock them in a fixed position. The second one is the two carbon atoms of the double bond and four atoms or the group of atoms which will be attached to the double bond, they all lie in the same plane. Why? because each of the carbon atom is sp2 hybridized. And the geometry of sp2 hybridized carbon atom is always triangular planar. The rotation is not possible across this double bond as it would weaken and break the pi bond. Now students, you can see in this picture, if one would try to rotate the double bond, it is going to twist, the pi bond will get weaker and is ultimately going to be broken down. So the alkene is going to lose its identity. Therefore, the rotation across this double bond is restricted due to the presence of pi bond which overlaps sideways. Therefore, the phenomena of cis-trans isomers exist in alkenes. Now students, let us try to understand this phenomena by another example. Consider two boards and two nails. If we are going to drive an iron nail through these two boards and try to rotate one board with respect to the other, the first one is fixed on its position and we are going to rotate the second board, it is easily going to rotate. So the free rotation is possible when we are driving one nail through these two boards. But now, if we try to drive another iron nail, the second nail, through these two boards and then try to rotate one with respect to the other, keeping the first board on its position, if we try to rotate the second board, it is not going to freely rotate. The same phenomena occurs in alkenes after the formation of a pi bond, that the free rotation is restricted. That is why cis and trans isomerism exist in alkenes due to the restriction in the free rotation across the double bond. Now students, let us see how do we classify cis and trans isomers. Cis isomers are those in which two similar groups are on the same side of the double bond, whereas trans isomers are those in which the two similar groups are on the opposite side of the double bond. Consider the example of cis and trans 2-butene. This is cis 2-butene. You can see that the similar or identical groups are present on the same side of the double bond. Whereas in the trans isomer, the identical or the same groups are present on the opposite side of this double bond. You can see the difference in physical states also. The boiling point of cis 2-butene is 4 degrees Celsius, whereas that of trans butene is 1 degree Celsius. Students, as we know that rotation of the double bond is restricted, so a cis isomer cannot be transformed into a trans isomer just by rotating it across the double bond. So if one wishes to transfer or convert cis isomer into a trans isomer, what are the conditions that we have to provide? The conversion of cis isomer into trans is possible only if either isomer is heated to a high temperature or in the presence of UV light. The heat provided, which is about 62 kilocalories per mole, is required to break the pi bond so that the sigma bond rotation is possible. Upon cooling, the reformation of the pi bond can take place, giving a mixture of trans and cis alkenes. Now look at this picture. You can see this is a cis isomer. When we are going to heat it, it is going to weaken the pi bond and ultimately it is going to break the pi bond. Now two possibilities can exist. When the sigma bond is going to rotate like this, the methyl group is going to move above the double bond and hydrogen below, which was initially present below the double bond. Now you can see upon cooling, if it is going to cool right after the rotation, it is going to give you a trans isomer. But if the pi bond is going to be broken down and rotation is not taking place, it might cool down and give you the same isomer, which is the cis isomer. So therefore we can say a mixture of cis and trans alkenes is going to form. Students, we have already discussed in the stability of alkenes that transalkenes are more stable than cis-alkenes due to the reduced steric interaction among the alkyl or the bulky groups. As you can see, the two alkyl groups are present on the same side in cis-alkene, whereas they are present far apart opposite to each other in the transalkenes. Students, how this reduced steric interaction develops stability in a molecule. In a cis structure, you can see that these two methyl groups, they are going to interact with each other. This steric crowding over here on this double bond is going to affect the stability of the pi bond and is going to react in order to convert the more reactive pi bond into a more stable sigma bond. But such type of interactions are not present in the trans structure because these two bulky groups, they are far apart from each other and hence they are not going to produce their effect on the double bond and giving more stability to trans structure as compared to cis. Now students, let us see what are the conditions for the geometrical isomerism in alkenes. As all alkenes do not show geometrical isomerism. Geometrical isomerism is possible only when each double bonded carbon atom is attached to two different atoms or group of atoms. For example, consider the case of propene. No geometrical isomers are possible for propene. This is because one of the bonded carbons has two identical groups, that is hydrogen atoms attached to it. Now this is the double bonded carbon atoms. You can see this carbon atom is having two same groups above this double bond and below this double bond. So cis and trans isomerism is not possible in such type of alkenes in which the double bonded carbon atom is attached to the same or identical atom or groups of atoms. Students, let us study some examples of geometrical isomerism. Consider the case of 3-hexene. Cis and trans isomerism is possible in 3-hexene because each of the double bonded carbon atom is attached to two different groups, that is an ethyl group and hydrogen. The cis and trans isomers of 3-hexene are as follows. Now you can see that in cis-3-alkene, the two identical alkyl groups are on same side of the double bond and hydrogen atoms on the same side. Whereas in the trans isomer, you can see the identical groups at opposite sides of the double bond. That is why cis and trans isomerism is possible in such type of alkenes. Students, consider another example of geometrical isomerism, which is butane dioic acid. Now what is a dioic acid which is having two carboxyl functional groups? Geometrical isomers are possible in butane dioic acid because each of the double bonded carbon atom have two different groups attached to it, that is a hydrogen atom and a carboxyl functional group. This is trans-butane dioic acid. As you can see across the double bond, the two identical groups are present on the opposite sides of this double bond. Whereas in cis-butane dioic acid, the two identical groups are present on the same side. The trans-butane dioic acid is called fumaric acid and cis-butane dioic acid is called malic acid. You can see the difference in the physical properties. The melting point of fumaric acid is 130 degrees Celsius, whereas that of malic acid is 288 degrees Celsius. Now students, let us study geometrical isomerism in cyclic compounds. Geometrical isomerism is also possible in cyclic compounds because there can be no rotation about the sigma bond, the carbon-carbon bonds forming a ring, because rotation would break the bond and break the ring. For example, 1,2-dimethyl cyclopropane. It exists in two isomeric forms. As you can see, the two methyl groups are above this plane on the same side. That is why it is called cis 1,2-dimethyl cyclopropane. Whereas in the trans isomer, you can see that two identical groups are on the opposite sides of this ring. Above the ring, you can see a methyl group and a hydrogen atom, and below the ring, you can see a hydrogen atom and this methyl group. That is why it is called a trans isomer. Now students, just like alkenes, the requirements for geometrical isomerism in cyclic compound is that there must be at least two other groups besides hydrogen on the ring, and these must be on the different ring carbon atoms. For example, no geometrical isomers are possible in 1,1-dimethyl cyclopropane. Why? Because on these carbon atoms there are two identical hydrogen atoms, and on this carbon atom there are two identical methyl groups above the ring and below the ring. So we cannot identify it as cis or trans isomers because of the presence of identical groups on same sides of the ring. Now you can see 1,2-dimethyl cyclopropane. It is having two methyl groups on separate carbon atoms which are adjacent to each other. Therefore, isomerism is possible. This is cis 1,2-dimethyl cyclopropane. And if this methyl would be below this plane, it would be the trans isomer. But if we transfer this methyl below the ring and this methyl above the ring, it is not going to make any difference. That is why in such compounds, cis and trans